Yeah.
Can you see it?
Yes, yes. So can you move your slides to see if it works properly?
Okay. Yeah.
Okay. Okay. So this is the third talk of the first session of this workshop. And Rongjin Miao is going to tell us about Codimension-n holography for wedges and cones. Please, Rongjin.
Hi, everyone. First of all, I will thank the organizer to give me the chance to talk about my recent work on the wedge and co-holography. Okay. And this work is based on these two papers. Okay. And first of all, I will give a review of holography and talk about the so-called Codimension-n holography for wedges, recently proposed by Takagi. And then I will talk about my results. I give an exact construction of the so-called wedge holography and show that the wedge holography can give the clocked Weyl anomaly, Rényi, entropy, and correlation functions. And then I will generate the wedge holography to the most general case, the so-called Codimension-n holography for co. And finally, I will summary and with some open questions. And according to Taubt and Susskind, there is a no duality between the higher dimensional gravity and the lower dimensional gauge field theory. And the first realization of the holographic principle is dCFT, which is proposed by Melasina that the quantum gravity in the bulk is due to the conformal field theory on the boundary. And after that, there are many interesting generalizations for dCFT, such as the dCFT and dCFT, flat holography, and Brain-word holography, BCFT, and the W holographic model. Here, BCFT is a conformal field theory defined on a manifold with a boundary. Here, B means boundary. And the W holographic model are recently proposed for the resolution of the black hole information problem. Actually, the Brain-word holography and the BCFT and the W holography model are very similar. And they have very similar geometry, and they are developed for different purposes. And the co-holography and the wedge holography in this talk are closely related to the Brain-word holography, BCFT, and the W holographic model. Now to turn to the geometry of the Codimension-n holography or wedge holography. Here, N is the bulk space, is the bulk ADS space, and Q1, Q2 are two underworld brain at the boundary of the bulk N. And the sigma is the corner of this wedge. And the so-called wedge holography conjectures that the gravity in the bulk N is due to the quantum gravity, okay, on the brain Q1 and Q2, and due to the conformal field theory on the corner of the wedge. Actually, the wedge holography can be derived from the so-called ADS-BCFT by taking in suitable limit. Here, this is the picture for ADS-BCFT. Okay. And M is the manifold where BCFT is defined, and the sigma is the boundary of M. When we take the limit M to 0, we can derive the wedge holography from ADS-BCFT, okay, by taking the limit M to 0. Okay. And this is the main idea of wedge holography. It's conjectured that the classical gravity on the wedge is due to the quantum gravity on the end of order brain Q, and due to the conformal field theory on the corner of the wedge. So as we return to this figure, the classical gravity in the bulk N is due to the quantum gravity on these two kinds of brain Q1 and Q2, and is due to the conformal field theory on the corner of the wedge. And the action of the wedge holography is given by this. And the first term is just the Einstein-Hilbert action in the bulk N. And this term is just the Gibson-Hawking term on the brain. And the T is the tension of the brain. The central problem in the construction of wedge holography is to determine the location of the brain Q. And it turns out the location of the brain Q can be fixed by imposing suitable boundary conditions. And this guy proposed to impose new boundary condition on the end of the brain on the brain Q. So from this new boundary condition, one can fix the location of the brain Q, and we can also fix the bug solutions. So this is the main idea of wedge holography. Let's make some comments on wedge holography. First, the first equivalence that the classical gravity on the wedge is due to the quantum gravity on the brain is just due to the brain world holography. And the second equivalence, this one, and the quantum gravity in the ADS space is due to the CFT and the boundary of ADS is just the usual ADS CFT. And the wedge holography is very similar to the so-called W holography, which is developed for the resolution of the information paradox. And it can be regarded as the special limit of ADS BCFT with vanishing strip Weiss. Okay, we have showed before. Okay, and the wedge holography can be derived by taking the limit m to 0 from ADS BCFT. And there are many support for the proposal of wedge holography, such as the Weyl anomaly and the entanglement entropy. For example, one can calculate the holographic Weyl anomaly for wedge holography and it takes this form for 2D CFT. Okay, for 2D CFT, it takes this form, and it takes the correct form and the Weyl anomaly of 2D CFT. Here, the central charge is proportional to this one. Okay, and one can present the central charge. Okay, denoted by C, and will satisfy the C theorem, and the C UV is larger than CIR. So this is the strong support for the proposal of wedge holography because it can produce the correct Weyl anomaly and the correct C theorem. And for simplicity, people mainly focus on locally ADS, and in this talk, we will study more general solutions to wedge holography. Okay. And in the talk, we focus on this kind of solutions. So in general, this solution is not ADS locally. And X is the distance to the brain. Okay, this is the to brain Q1, Q2, and this is the direction of X. So the X is just the distance to the brain, and the Hij is the induced metric on the brain. It's interesting that if Hij satisfy Einstein equations in on the brain, okay, in lower dimensions, then the bulk metric J mu will satisfy Einstein equations in higher dimensions. So this kind of solution have defined a map from the solution to Einstein equations in ADS CFT to the solutions to wedge holography. Okay, and one can check that this metric satisfies the new one boundary condition. Okay, this satisfies this kind of boundary condition. Okay, K minus T and Hij equals 0. And for the brain is located and X equals plus and minus rho. Here rho is the constant which is related to the tension of the brain. So in a word, this metric is a solution to wedge holography. Okay.
Sorry, before going on, may I ask a naive question?
Okay, please.
So, sorry for the interruption. In the usual ADS CFT, I mean, at least the first derivations, one started with some solution corresponding to a stack of branes and took some decoupling limit. And the very fact that this decoupling limit existed was crucial for having the next steps that the duality makes sense and so on. I was wondering whether similar decoupling limit also makes sense in your setup. Can we argue that there is a decoupling limit close to your codimension-1 branes or codimension-2 corners?
Okay. In this theory, we just focus on the classical gravity in the bug. So I guess it's similar to the Euro case in dCFT. So in this talk, we only focus on the gravity in the bug and is classical. Okay. And we focus on the large n limit. Okay. Do I answer your question?
So
I think the situation is very similar to the Euro ADSLT. Okay.
So basically, you're saying that let's start with a stack of n branes on top of each other, and one separated a little bit, or two separated a little bit, and then take the near horizon over the stack, such that the remaining branes are living on an ADS, or I just don't see how this may work. Sorry for the interruption.
This is the ADS boundary. Okay. Okay, and M is just the ADS boundary. So usually the brane is located under the ADS boundary here. But for our case, we put the brane, okay, into the bulk like this. Okay. And we take the limit. So seeing the right figure, we have three kinds of brane. Okay, this one and this one and this one. And this brane is just the ADS boundary. And we take the limit to make this kind of brane disappear. And to get the geometry of Wedge holography.
Okay, so maybe I need to wait until the end of the talk, but the question is whether there exists a decoupling limit. If the gravity is not decoupled, which I think it is not, then we'll not have this full duality codimension or codimension-2 type of holography that you're talking about. So maybe I should wait until the end of the talk. Sorry for interruption.
Okay, let me continue. So we have chosen this metric is the solution to Wedge holography, and we put this metric to the the bug action. And after some calculation, we find the action take the exact form the Einstein selection in ADS space. So the Wedge holography with this kind of solution is equivalent to dCFT with vacuum Einstein equations. And the effective unit constant is given by this integral. Here we call that rho is the tension of the brane. Okay. It should be mentioned that this kind of solution is not the most general solutions to Wedge holography. Okay, right? It's not the general solution. Okay. So only for this special kind of solutions, we can prove that the Wedge holography is equivalent to ADSLT. But in general, the Wedge holography and ADSLT are different. So the equivalence to the ADSLT can be regarded as a proof of Wedge holography in a certain sense. And the reason as follow: we assume ADSLT hold. So the classicality in ADS space is due to the conformal field theory on the boundary, and we have just proved the equivalence between the two actions. So we have just proved the classical gravity on the wedge. the classical gravity on the wedge is due to the is equal to the classical gravity in the ADS space. So from equations 9 and equation 10, we can prove the classical gravity on the wedge is due to the CFT on the corner of the wedge. So we give a proof of wedge holography, at least for this special kind of solutions. Okay. Let's make some comments on the equivalence. And the equivalence still hold after the holographic renormalization. Okay, so we can enter the counter terms on the corner of the wedge, and the equivalence still hold after we enter the counter terms. And due to the equivalence, now most results of dCFT apply directly to wedge holography. So we can derive Weyl anomaly and the Rényi entanglement entropy and correlation functions. And in general, the wedge holography is equivalent to dCFT with a massive gravity instead of Einstein gravity. That's because then because the KK mode, okay, the KK mode on the brain are massive generally. So in general, the effective gravity on the brain are massive gravity instead of Einstein gravity. Only for this kind of special kind of solutions, the effective action on the brain is Einstein gravity, but in general, the effective action on the brain are massive gravity. So in general, the wedge holography is expected to be equivalent to dCFT with massive gravity. Okay. Now let's test the wedge holography by study Weyl anomaly and entanglement Rényi entropy. The Weyl anomaly measures the breaking of the scale symmetry of conformal field theory due to the quantum effects. And in general, the Weyl anomaly is given by this formula. Here, E2P is the Euler density, and In are conformal invariant terms, and A and B are central charges of Weyl anomaly. The A-type central charge will satisfy a C-like theorem. So we have A UV is larger than A AR. And the Weyl anomaly is closely related to the universal term of entanglement entropy, the UV log diagonal term of entanglement entropy. From Weyl anomaly, we can derive the universal term of entanglement entropy as this. Here A is just the A-type central charge. Now let's turn to discuss the holographic Weyl anomaly in wedge holography. Okay. In general, the holographic Weyl anomaly can be obtained from the UV log diagonal term of the effective action. So we take the ansatz of the metric, and the sigma ij is given by this. And from the Barker-Einstein equation, we can solve sigma 1, sigma 2, and so on. So we put this solution into the gravitational actions, and then we select the UV log diagonal term of the effective action, and then we can derive the holographic Weyl anomaly. We find that it takes this form, and with the central charge A is given by this. So now we have derived the A-type central charge for wedge holography. It's given by this formula. Here, recall that rho is related to the tension of the brain. Okay. So now we turn to the holographic C theorem for wedge holography. As we have just mentioned, the C theorem implies that AUV, the A-type central charge, AUV is larger than AAR, and the A-type central charge is given by this formula. Okay. Given by this formula. Here, this term is a positive function. So we have the A-type central charge increase with rho. So A increase when rho increase. Here, rho is the tension of the brain. And from the non-ideal condition on the brain, we can prove that rho UV is larger than rho AR. So from this relation we have AUV is also larger than AR. So from the null analytic condition, we can prove the C theorem for Wedge holography. Actually, there is a very clear geometry picture for the reason why rho UV is larger than rho IR. Recall that rho is the tension of the brane, and rho is related to the angle between the brane, okay, and the ADS boundary M. The smaller the tension rho is, and the larger this angle is, and the deeper the brane turned into the bulk. Okay, so the smaller rho is, the deep the brane turned into the bulk. So this is the smaller rho, and this is the larger rho. And we know that in the bulk is just the UV, and in the ADS boundary is corresponding to the IR. So we have the rho UV is larger than larger than rho IR, and then we can prove AUV is larger than AR. Then we find a proof of the C theorem in the framework of Wedge holography.
Excuse me.
Okay.
I joined your talk late, but this proposal works for D greater than 3 usually, not for lower dimensions. No, you don't pass to the limit of D equal 2. No.
You mean D equals 2?
The dimension of the bulk. In your case, never goes to the below the 3,
yeah.
Never goes below 3.
The dimension of the bulk is larger than 4. Okay.
Ah, 4. Okay.
Okay, larger than 4. Okay. And the CFT is just the two-dimensional CFT. Okay. So now let's turn to the Rényi entropy. Rényi entropy is the generalization of the entanglement entropy, and is the complete measure of the quantum entanglement. And the Rényi entropy is defined by this formula. Here n is a positive number, and rho A is the induced density metric over subregion A. For example, we have a subregion A and its complement, and if we focus on the subregion A, we can define an induced induced density metric by this formula. And then from this formula, we can calculate the Rényi entropy, and it contains all the information of quantum entanglement. Okay. And in the limit n equals 1, the Rényi entropy reduced to the entanglement entropy in this limit. In the holographic theory, the holographic Rényi entropy can be calculated by the air or the cosmic brane. So, for example, this is the ADS boundary. Okay, we have a subregion A, and the Rényi entropy can be calculated by the air or the cosmic brane here. Okay, this is the cosmic brane. Okay, and in general, the tension of the cosmic brane is non-zero. So in general, there are backreactions to the geometry. So in general, it's very difficult to solve Einstein equations with non-trivial cosmic brane. But if the subregion A is a C-sphere or half space, then we can solve. Then one can find solutions. So we focus on the special case where the subregion A is a C-sphere. Okay. So this is the formula for the Rényi entropy in the usual dCFT. And what's new for the Wedge holography is that now the cosmic brane can end on the end of word brane Q, Q1 and Q2. So what's new here is that the cosmic brane here can end on these two kinds of brane. Note that the Q1 is a codimension-2, the boundary codimension. Sorry, the Q1 is codimension-1, but the cosmic brane is codimension-2. So they are different branes. Okay. This is the answers for the the answer for the metric. So we suppose there is a hyperbolic black hole on the brain, and RH is the horizon of the hyperbolic black hole, and the Rényi index n is related to the temperature of the black hole, and the cosmic brain is nothing but the horizon of the black hole. So from the metric, we can calculate the air of the horizon, and then from this formula we can solve the Rényi entropy Sn, and it takes the form. Here Vh is the volume of the hyperbolic space.
Excuse me, this normal derivative of normal derivative of the Rényi entropy can be interpreted in terms of the concept of complexity. We can interpret that. What is the physical meaning of the partial derivative of the Rényi entropy?
Here?
Yeah. What is the physical meaning of the left side? This partial n. What is the physical meaning of that? I understand that when n and the limit of n goes to 1, this is a derivative of the entanglement entropy. What is in the general? What we can say in general?
Okay, in general, this is like this because n is related to the temperature, right? So the left is just the temperature and the F. Okay.
Which temperature is that? This is the entanglement temperatures, or what kind of temperature is this?
Okay, it's just the temperature of the hyperbolic black hole, right? Okay. And for this example, so n is related to the temperature of the hyperbolic black hole. Okay. And in general, the left hand is just like the partial T, and the F is just the free energy. Okay. So you can see you can see on the paper. Okay. So this formula indeed have a very clear physical picture. Okay. So the left hand is something like the partial T F. F is the free energy of the theorem. The free energy. Okay. Let me continue. So we have derived the Rényi entropy for Wedge holography that takes this form, and in some special case, for 2 dCFT, the Sn takes this form, and it has the correct n dependence. And in the limit n equals 1, okay, the limit n equals 1, and the Rényi entropy reduced to untitled entropy. It takes this form, okay, and from this form we can derive the universal term of untitled entropy. Here V is the volume of the hyperbolic space. It includes an UV log divergent term. So from this term we can derive the UV divergent term of untitled entropy, and it agree with the results derived from Weyl anomaly. So we have 2 methods to derive the universal term of untitled entropy. First from Weyl anomaly, and the second from the Rényi entropy, and they agree with each other. And similarly,
the holographic interpretation of Rényi entropy, interpretation of Rényi entropy exists and understood only at to 1. If n doesn't tend to the 1, so then the Rényi entropy, in my knowledge, doesn't have any holographic interpretation. Is it right? So
no.
I mean
no. N applied to general case. You take n to any positive number larger than 1, larger or equal than 1. Maybe you can see on the paper, okay. So n is a general positive number larger or equal to 1. And if n is larger than 1, then the cosmic brain will have a non-zero tension and it will have a back reaction to geometry. Okay. Okay, let's go on. And similarly, we can also derive the correlation functions. Okay, and okay. Now let's turn to the to generalize the Wedge holography to more general case. First, I will give a new viewpoint of Wedge holography. Actually, the Wedge holography can be regarded as a special as the holographic dual of the edge mode on the boundary. The reasons are the follow. Take a three-dimensional BCFT as an example. The Weyl anomaly is given by this form. Okay. The first term is just the Weyl anomaly of 2D CFT. Okay. It's just the Weyl anomaly of 2D CFT. And what's more, the central charge B1 satisfies a C-like theorem. We have B1 UV is larger than B1 IR. So this strongly implies that the effective theory on the boundary are CFT. So this implies the Weyl anomaly implies that the edge mode on the boundary is an effective CFT. However, the edge mode also include the bulk informations because the Weyl anomaly depends on the extrinsic culture. So it also includes the bulk information. So the edge mode is different. Okay, different from the Euro CFT, right? So it's very similar to the Euro CFT, but different because it includes bulk information. So the holographic dual of the edge mode will be different from the Euro holographic dual of CFT. So it is expected that the holographic dual of edge mode is different from ADS CFT because this kind of CFT also includes bulk information. Okay, it includes more information than the Euro CFT. And what's the holographic dual of the edge mode? Okay, the answer is Wedge holography. Okay. Here I'm is the sorry. Here M is the manifold where BCFT is defined. Okay. M is the manifold where BCFT is defined, and the sigma is the boundary of M, and there are edge mode on the boundary of M. And the edge mode behave effective as a CFT. And in the limit M to 0, okay, in the limit M to 0, and the BCFT disappear, and only the edge mode on the boundary survive. So in this limit M to 0, we only have edge mode, okay, on the boundary. And this picture is the holographic realization of the above picture. And according to ADS BCFT, and the boundary sigma is extended to the bulk boundary Q, and Q2 and Q1. And between the limit and according to the Euro ADS, okay, ADS BCFT, the classical gravity in the bulk N is due to the BCFT on the manifold M. However, if we take the limit M to 0, okay, the Euro BCFT disappear and only the edge mode, okay, the edge mode survive on the boundary. And then according to ADS BCFT, the classical gravity in the bulk N is due to the edge mode on the corner sigma. So this is the main idea of Wedge holography. So in this sense, the Wedge holography can be regarded as a holographic dual of the edge mode on the boundary. Okay. So our motivation is very simple. We want to generalize the above discussions to the most general defect CFT. Recall that the boundary is a codimension-n defects. So can the above discussion be generalized to the most general codimension-n defects? The answer is yes. Take a 4-dimensional dCFT with a codimension-2 defects as an example. The Weyl anomaly is given by this formula. This is the Euro bulk Weyl anomaly, and this is the Weyl anomaly on the defects. Okay, and similarly, the first term take exactly the form of Weyl anomaly for the Euro 2D CFT. Okay, 2D CFT. So the first term is just the Weyl anomaly with the Euro 2 dCFT. And what's more, the D1, the central charge D1 also satisfies the CDX theorem. We have D1 UV is larger than D1 AR. So this strongly implies that the edge mode on the defects is an effective CFT. And similarly, the edge mode includes more information, and they include the bulk information, such as the Weyl tensor and the extensive curvature. So our main purpose is to find out the holographic deal or the edge mode on the general defects. Okay. So this is the main purpose and the motivation of this talk. Okay. We want to have a well-defined zero-volume limit to take the volume of dCFT to be 0. And to have a well-defined zero-volume limit, we should add an additional boundary P. So M is the manifold where dCFT is defined, and P is the boundary of M, and D is the codimension M defects and the center of the manifold M hat. And we require the boundary to have the geometry to be S cross R. Here S is a sphere, okay, and the defect is just R D minus M. Here R D denotes flat space. And then in the limit M hat of 0, we require the sphere, okay, to vanish to 0. So in this limit, this term vanish, and the boundary approach the defects in this zero volume limit. So this is the main setup of the geometry. Okay, and then in the limit M to 0, the Euro dCFT disappear. Okay, and only the edge mode on the boundary P and on the defects survive. So in the limit M to 0, we only have the edge mode on D and on P. And below is the metric for the above finger. Okay. Here, the defect is under z equals 0, and the boundary is under z equals 0. Here z0 is a constant, and at the end we take the 0 to 0. So in the limit z0 to 0, and P becomes the defect D. Okay, in this limit, and in this limit only the edge mode survive. Now this is the holographic realization of the above picture. Recall that M hat is the manifold where dCFT is defined, and P is the boundary of M, and D is the defect and the center. According to ADS BCFT, the boundary P is due to the bulk boundary Q, the end of Brain. So according to ADS BCFT, the P is due to the bulk boundary Q. And according to the Euro ADS dCFT, the defect CFT, the defect D is okay. This is P. The D is due to the codimension M Brain E. Okay. And so according to the Euro ADS BCFT and ADS dCFT, the gravity in the bulk C is due to the defects, the defect CFT on the boundary M hat. Okay, and in the limit M hat of 0. Okay, we have the P approach the defect D, and only the edge mode survive on these defects. So the edge mode survive on the defects, and in the limit, we can derive the so-called co-holography that the gravity in the bulk C is due to the edge mode on the defects D. Okay. So this is the main idea of co-holography. So in general, it's a holographic deal with the edge mode on the general defects, and it can be derived from a limit of the Euro ADS dCFT, and similar to and it's very similar to the case of Wedge holography. Okay. After take the limit m had 0, we have these pictures. Okay, so this is the geometry for the co-holography. And the co-holography supposes that the gravity, the classical gravity in the co C, okay, is due to the CFT on the defects D. Here E is the codimension M defects. Here M equals n minus 1. Here E is a codimension M brane, and Q is a codimension 1 brane. And the geometry of E is said to be ADS, and the geometry of Q is said to be ADS cross a C-sphere. So that the boundary of E and the boundary of Q are the same. So we have the defects is the equal to the boundary of the brane E, and is also equal to the boundary of the bulk boundary Q, because the boundary of this C-sphere is one-ish. Okay. And this is the metric for the co-holography. Here R is a distance to the brane E. Here this R direction. So R is a distance to the brane E. Here this is the brane E. And Z is the ADS coordinates. Okay. So the brane E, so the brane E is located at R equals 0, and the brane Q is located at R equals R0 or R equals F omega. Here, here omega is the angle. Okay. And the defects, and the codimension M defects is located at R equals 0 and Z equals 0. Okay. So this is the geometry of the co-holography. Okay. And this is the general action for co-holography. Okay, and it's just the Einstein spectrum in the bulk C, and the Gibbs term on the brane Q, and T is the tension of the brane, and T is the tension of the brane E. Okay, the central problem in the construction of the co-holography is to determine the location of the brane E and the brane Q, and we propose the brane E is given by the minimal surface. Okay. So the brane E here is given by a minimal surface, and the brane Q can be fixed, and the location of the brane Q can be fixed by boundary conditions. So we consider the variation with action, and it's given by the boundary conditions. Okay. Wait. So the compiler have some problem. Let's see. Okay. Recognize the geometry of Q is given by the ADS cross a C-sphere, and we want to have a dynamical gravity on the ADS sector. So we want to impose the new one-bound condition on the ADS sector. So in general, the metric on the brane Q is given by this. Here, HAB is the metric of the C-sphere sector, and the HIJ is the metric of the ADS sector. We want to impose new one-bound conditions on for HIJ in order to let the HIJ to be dynamical. So in general, we have two kinds of bound conditions. The first is the full new one condition, and the second one is the so-called mixed bound condition. Then we fix the new one condition for HIJ and the delicate bound condition for HAB. And the general solutions, okay, we consider a special class of solutions to co-holography. Here, H bar Ij is the induced metric on the brane E, and we require H bar Aj satisfy Einstein equations on the brane E. And F and J can be solved by the bulk Einstein equations. The brane E is located under R equals 0, and the brane Q is located and for Newman bounding condition is dependent on the angle, and for the mixed bounding condition, R is equal to a constant. So we consider this class of solutions, and we put this solution into the bulk action. Into the action of Wedge holography, and after some calculation, we can derive. And the co-holography with this kind of solution is equivalent to the dCFT with vacuum Einstein equations, with vacuum Einstein gravity. And the effective Newton constant is given by this. And similar to the Wedge holography, the equivalence to dCFT can be regarded as a proof of the co-holography, and at least for this class of solutions, for this special class of solutions. And note that this is not the most general solutions to co-holography. Okay, so in general, so for the general solutions, the co-holography is not equivalent to dCFT with Einstein gravity. Okay. Let's make some comments on the co-holography. Co-holography can be regarded as a holographic dual or the edge mode on the defects, and it can be derived by taking suitable zero value limit of ADS dCFT. For one class of solutions, we have proved that co-holography is equivalent to dCFT with Einstein gravity, but in general, this is not the case. Similar to the Wedge holography, we can also derive the correct holographic Weyl anomaly and Rényi entropy and correlation functions for the co-holography. And we can show that co-holography also obeys the holographic C theorem. And we have mentioned in general, co-holography is different from the usual dCFT, and it's expected to be equivalent to dCFT with massive gravity instead of Einstein gravity, because the key mode on the brane Q is the massive generally. So now turn to the holographic C theorem for co-holography. The central charge, the A-type central charge for co-holography is given by this formula. Here, F and J are two positive functions. So we also have the A-type central charge increase when the tension rho increase. And from the non-ending tension on the brane, or from the above, or from this geometry picture, we have rho UV is larger than rho R. So we have A UV is larger than rho R, A AR. So we can prove the C theorem for co-holography. Okay. Now let's summary. In this talk, we give an exact construction of Wedge holography and prove that it's equivalent to dCFT for one special class of solutions. And we proposed a Codimension-n holography called co-holography, that a gravity theory in the d+1 dimensional co is due to the CFT on the d+1 minus n dimensional defects. And Wedge holography and co-holography can be regarded as a holographic dual of the edge mode on the defects, and it can be derived by taking a suitable limit of the ADS dCFT. And they then give the correct Weyl anomaly, Rényi entropy, and correlation functions. And in particular, they obey the C theorem. So in the talk, we focus on a special class of solutions. So in future, it's interesting to study the more general solutions to Wedge and co-holography. In this talk, we only focus on the massless mode of gravity. So in future, it's interesting to study the massive mode on the brane. it's also interesting to study the island and the particle or hybridization in the framework of co-holography and Wedge holography. Okay, thanks.
Okay, thank you for the talk. Are there any questions or comments to the speaker? Okay. So let me ask a couple of questions.
Please.
Do you have any idea whether this kind of Codimension-n holographies could be embedded in string theory? Or whether supersymmetry plays any role here, or can you have a supersymmetric version of this?
Okay, this is a very good question. But for you mean the supersymmetry? I guess so. Usually, if the bulk action, if the bulk gravity is Einstein gravity, then it's due to a CFT with supersymmetry. So but now the effective action on the brain is not Einstein gravity, but it's a general or massive gravity. So I'm not sure if one can have a CFT with supersymmetry. So this is an open question. Okay. Okay.
Okay.
And in the string theory, I guess so. Because for the co-holography, there are two kinds of brain. Okay, there are codimension, okay, a codimension-n brain, okay, and a codimension-1 brain Q. So it maybe can be related to string theory by adding these two kinds of brain suitably. So this is also an open question. Okay.
Yeah. So and as one last question, if I may,
okay, please.
I was wondering what happens for the specific case of two-dimensional gravity and three-dimensional gravity. So your codimension-1, so for example, if you have JT gravity, the bulk,
right,
then
okay.
your codimension-2 would be just a point.
Yeah, yes. So if the bulk is three-dimensional and the Q is
I just
so
even wanted to start. I wanted to start with two-dimensional case, ADS2, the JT gravity.
Okay. ADS2.
Yes.
So this is
and
ADS1, and this one just a point. Okay.
So ADS1 is just a line, and that's just a point in the space-time.
Right.
So does any of these arguments also work for this case? Because I don't know what a one-dimensional gravity is to start with. So maybe
yeah. Tadasi have considered this problem in that paper. And if the gravity in the bulk n is Einstein gravity, then the theory is kind of a theory. Then the theory is kind of a trivial. But if you consider more general gravity, okay, For example,
well, here in 2 dimensions we
right,
have JT gravity. It's metric plus scalar.
Right. If you consider the JT gravity, okay. And I guess okay. Tadase only consider Einstein gravity. Okay. For Einstein gravity, the theory is trivial, but for JT gravity, this maybe have non-trivial dynamical, okay, on Q and maybe on sigma.
So, and similarly for ADS3 for 3-dimensional case. So if the original bulk is ADS3, then you'll have some ADS2 type gravity, something like a JT gravity probably. Then your sigma, the point is just one-dimensional time direction.
Right.
So I was just wondering how does it work for this case?
Okay, if we consider Einstein gravity in the bulk, okay, at the Einstein gravity, then it's just okay. So it's also Einstein gravity on the brane Q. So it's also trivial, okay, Einstein gravity.
Yeah.
So if we consider more general gravity, for example, something similar to JT gravity like this, then it will have similarly it will have a non-trivial dynamical on the brane. So for the Wedge holography, the non-trivial case is started from ADS4. Okay, if we consider the Einstein gravity in the bulk N, but if we consider the modified gravity in the bulk N, then I guess there are also non-trivial dynamical for ADS3. Okay, like this.
Okay, so any further questions or comments for the speaker? If not, let's thank the speaker again and all the speakers of this first session. And the conference will resume in a bit less than 10 minutes, less than 3 hours from now. Hope you can join then to the second session. Thank you, everybody. Thank you, the speakers. And for now, bye for now.